Hi, very good evening, everyone. Thanks a lot for joining in. For anyone who's on YouTube right now. We'll just take a few more minutes for everyone to join. I have shared the URLs to everyone. I believe all of you might have got the URL to join the session today. Just in case, to also share to across your friends or any of your WhatsApp groups that is somebody interested to take part in the session. And also, there are a lot of students or participants who are interested to join the session, but the session link was closed yesterday. We have reopened the link today. If in case any of your friends are interested to take part in those sessions and learn the part of this series of 5 days, surely they can still join the sessions too. All right, so let's just check the time. Yeah, it's 7:55, 4:53 right now. We'll just wait for some more time for everyone to join in, maybe just about another 6 minutes to go. In the meantime, if anybody have any questions from the yesterday's session, or if you'd like to put across uh, any anything as your interest to learn from today's session, so yes, please do go ahead and drop your questions in the chat box so that I would pick them up and we can have a quick interactive discussion for a few minutes. All right, so good evening to everyone. Joined here Abhishek, Atharva, Samiksha, Karan, Manoj, Harshit, Rajput, Ashwin, and Reshma. Right, so guys, if you have any questions that you would like to interact from the yesterday's or maybe even about today's topic, so do put them across in the chat box so we can just utilize a few minutes before our session to interact with all of us. Okay, so cool, people are joining in. Right, very good evening, everyone. Right, so yeah, 5 more minutes to go. It's 4:45 right now. Okay, just begin in this time. I'll just run through what we can take away from today's session, and what are the topics that are we going to touch base in the course due today. So, as everybody know, we're going to talk about the battery management system today. I would talk about the importance of battery management system. We'll also talk about architecture of a battery management system. And we'll also talk about certain functionalities, little in depth, also at a surface level too, because it's quite difficult to cover the topic very much in depth in the due time of 30 to 45 minutes. And then we'll also talk about what it takes to build a battery management system. If you want to be an engineer in the battery management system sector, I believe a lot of people are very much excited, and yes, there's a lot of questions from many people that to learn about battery management system. Um, so I have made a slide about what really happens if you want to develop a battery management system, and in that regards, what sort of skill sets that are required. So I've made a slide on that. So that may be interesting for many people who are eager to explore some of the opportunities in battery management systems. So yeah, and we shall talk a bit about algorithms, and also I would demonstrate something about the battery management system we're trying to develop at Decibels Lab along with partnership with Sloki. Yeah, so and then I'll also brief you about something that you can learn handy to jump in to explore your career in EV sector in the areas of battery management systems. So I hope that would be quite interesting for all the people who are participating here. We just have 2 more minutes before we just begin the session. Cool. As today, if anybody have a specific question or an interest or anything that you want to take away as a part of this today's topic on battery management system, just drop in a question. So that would be quite good for me to drive the session to possibly address those interesting topics that you're interested to know about. Okay, so we have about 40 people. So yeah, very good evening to everyone. Nilesh, Saurav, Jagat, and Dinesh. So all right. So Amol, thanks for joining again. Yeah, hi everyone. If you have any questions or something that you want to take away from this session today, so please do drop your questions in the live chat box. We just have 1 minute to go to start the classes, the session, I would say. Cool. So as everybody know that this is a very exciting topic for a lot of people because it's just exciting as it has been from quite some time. Everybody talks about becoming a battery management system engineer. Everybody talks about developing their own battery management system at company. So I believe in every different way, it's exciting for many people. Fantastic. So let's get started with today's session. Let me just put this for recording. All right. So very good evening, all of you. Thanks a lot for everyone to join into the session, which is day 2 of Foundation to Electric Vehicle Subsystems and Technology. As a part of this session today, so we will be discussing on battery management system, which is called as BMS. And yeah, it's just delivered by me. And let's just jump in ahead. So what is battery management system? It is an embedded hardware combined with application software and device drivers with some communication systems inside it. That is what forms the battery management system. So an typical battery management system looks like this, which will have various different components as a part of the battery management system. So if you see, which is in hardware as an architecture, it is having something you can call it as a master board, then it is having some slave boards, then you have a battery here, right? So we get cells as we discussed, which you also see here. And these cells are brought by Samsung and LG or Panasonic or A123 or anybody else as such in the market. So pack manufacturers would buy the battery management system, batteries from cells from various suppliers, and then they build a module, right? So in some cases, there is no module. So the configuration is directly cell and a pack. And in some cases, we have a cell, and then a module, and then a battery pack. All right. So in this case, which you see here on the right side of the screen, or the one part of the screen I've zoomed in here, there are cells here. They are integrated to form a module, and then all those modules are combined together. That forms the battery pack. All right. So maybe let's take an example that this is a 48 volt, and this is also a 48 volt, and this is also a 48 volt. So the scenario is maybe the end battery pack voltage can be 48, and so that the pack of 48s are in parallel. So maybe let's say this is 48 volt battery pack, and each is about 20 amp. So that forms about 60 Ah, the battery pack. All right. So you wanted to form a battery pack which is 60 Ah and 48 volt. So what you did is you divided that into individual modules of 48 volt 20 amps, and then you summed up them in parallel, and that is what made as a whole pack, right? So this is your pack, and then that you would have actually assembled all of them together to make as a one pack, but the pack become too large in size, right? So that's why you wanted to divide them into modules. So if you take Tesla, so there are many number of modules like this, because at some vehicles they have somewhere about 9,000 cells. So not 9,000 cells are connected in, all of them are connected in one single module. They've divided them to multiple modules of certain packs voltage and current. Sorry, module voltage and module current. Now, the objective of the battery management system is to do a lot of activities, right? So the battery management system, the very primary functionality of a battery management system is to manage the whole module or manage the pack, or to ensure that the cell, module, and also the battery pack remains in its safer condition. All right. So that's a very primary responsibility of a battery management system. The first, foremost primary responsibility of a battery management system is basically the safety. All right. So to ensure that it doesn't go beyond the safety limits. What are those safety limits? We will discuss about it in terms of current, in terms of temperature, in terms of voltage, also in terms of insulation. A lot of other things will come into a picture. So the form of factor safety is to ensure the cell do not crosses its limits. Okay, that's the primary requirement. So then on top of it, there are a lot of other activities which the cell, which the battery management system does. So we will discuss that in the later part of the discussions. So if you see here that there is it's basically an embedded hardware, which is coupled with application software and a device driver software with certain communication systems in place, and that is what forms the battery management system. So it's majorly in electronics, and obviously the part of application software is your control software or an algorithms that comes as a part of measuring various different estimation approaches, so estimation things. So we'll discuss all of that. So I believe you broadly understand what is battery management system is. So the BMS does come in various different architectures. So if you have a very simple battery pack, like an application like two-wheeler, all right. So the two-wheeler battery packs are like, it depends upon if it is a scooter or if it is a bike or if it is a super bike or something like that. So the pack capacity varies, all right. So it could be 48 volt, as simple as that, or something like what Aether has, the 51 volt, or even up to like 72 volt architecture, or even at super bikes it can go up to like maybe 400 volts, something like that. So the thing is, you need to connect all the cells to the battery management system that it can manage. So I think we would know, all of us know that the series and parallel configurations, right? So if you want to build a battery pack, so you can select a cell, and from the cell you can make them into a series and parallel configuration, and then you can go ahead to build a battery pack. So if you have a very simple, smaller battery pack, something like a 48 volt architecture, and somewhere like 60 amps or something like that, you can go for centralized architecture, all right? So if you have even up to 72 volts and let's say 60 amps or something like that, you can still go for a centralized BMS. All right. The centralized BMS is something where there is only one controller, which is basically the single controller. All right. And then you connect this controller to the cells, right? So which are in series and parallel configurations. So the architecture is again defined for the distributed architecture, which is something like this, where you would have, let's say, let's talk about an application perspective, where the centralized BMS and the distributed BMS will come into a picture. So this is a centralized BMS, and this is distributed. All right. Centralized BMS is good if it is an application like a smaller size, maybe like a 48-volt application or something like that. So if it's a smaller battery pack in a simplistic term, all right. So the distributed architecture is useful if you take an example like a bus, all right. So the bus battery pack is very large in size. Maybe you can just count about 100 kilowatt, right? Or if you take a truck as such. So what happens is like your battery is, if you take a bus as this big size, the batteries are distributed across various place of components. Maybe the battery pack is here, some part of the battery packs are here, and some battery packs, some modules are here. Let's just define technical term. So you want a battery management system that is able to connect to all of these modules and then perform the computation, right? So let's take the BMSs here. So if you want to run the set of wires to connect to all of these modules, right? So let's say each module is 48 volt, and let's say this is in 13 cells in series. So on average, you require about 15 wires for each of these modules, all right? So there are 15 wires coming from this module. This is counting these numbers, right? So imagine there are 15 again coming from this, and 15 coming from this, right? So it becomes very, 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 very clumsy if you want to run a set of wires, because you want to monitor the cell voltage, you want to monitor the cell, like the temperature of the module, you want to monitor the current and various different parameters of the cell. So what happens is it becomes too much of a wiring stuff if you try to connect all of these cells with a battery management system. All right. So this becomes like a very painful task to perform this wiring. And also, if you see if you know, like the basic electrical resistance, so if the length of the wire is large, obviously the resistance is also more. So then if you measure, let's say 3.2 volts, there may be a drop in voltage by the time you read at the circuit or a controller, because you have a resistance on the path, right? So you would possibly read like 3 point something like 19 0, something like this. So the voltage at cell is 3.2, but the voltage read at your controller is 3.190. It's because there's a voltage drop because of there's resistance in this wire, and this wire is too long from the BMS. So this becomes a difficulty thing, for you to, what I say is designing the centralized battery management system. So now what you do is you go for a other architecture, which is just take a bus as such now, and so you have a lot of modules which are here, and let's say there are a lot of modules here, and so this is an example of a distributed battery management system. So where you can have one centralized BMS, all right? So you can have a slave BMS which sits here, all right? So then this slave BMS has the wiring going to this, and then this slave BMS is interacting with a module. So this is a module, right? So then they have an interconnectivity using something called as a daisy chain network, all right? So then it's possibly like a CAN communication protocol or something like that, or TCP. any type of communication protocol. So I think you would understand this image, and I know it's not very neat and clean. So what happened is here that you have a slave BMS, which is sitting here on the module. So each module will have a slave BMS, and all those slave BMSs are connected together through like communication protocol. Maybe it could be something like a CAN-based communication protocol or any other type of protocol that has been well proven for automotive requirements. And nowadays, you also have wireless, which is possibly either they are connected through a Bluetooth or they are also connected through a Wi-Fi network or something like that. But I think still I don't see anything really available in the market. I mean, implemented in the market commercially, but today we all have wired communication currently. So now if you see the whole wiring, it is quite simple in nature, right? And this is the advantage of a decentralized battery management system. So it depends upon your vehicle requirements. So either if your vehicle requirement is very small, so you can go for a centralized BMS, or you can go for a distributed BMS. So the BMS would something look like this, which is a daisy chain based distributed architecture. So you have one master and you have multiple slaves, all right? That comes as like this. So the slaves do not perform any computation. The computation is like there is no processing that is happening in the slave, all right? The slave is just collecting the data, and the data has been sent uh, to the master BMS, and inside the master BMS, we will have all the computations, all right? So it is just collecting all this, slave BMSs are collecting the data, and then they are pushing the data to the master. And in the master where the calculation happens or the processing happens, all right? So this is good because if you want to build a larger size, you can call it a scalable battery packs or a scalable battery management system. So you could go for a distributed architecture. So just to revise from the beginning, so the battery management system is an embedded hardware, which is basically an electronics, which is coupled with an application software, which takes care of all the control functionality or all the estimation functionality, all the safety functionality or diagnostic functionality as such of the battery management system. And then it combines with the device drivers, because you need to interact with a controller. So application software, and then the device drivers, and then the embedded hardware. So all of them sit together as the BMS. So the primary functionality of a BMS is to take care of the safety of the cell and also perform various other activities and such. So the battery management system can be centralized BMS, or it can be also a distributed BMS. So we have gone through the various application nodes that where the centralized BMS can be used, where the distributed BMS can be also used, right? So then if you see the largely as a functionality, so what exactly the battery management system does. So the battery management system does many of these activities as such, which is mentioned here. So the very important activities, it takes care of the batteries or a cell's voltage, all right? So it measures the voltage of the cell. So we can't actually measure the voltage of each cell. We measure the voltage across a parallel circuit. So let's say you have a battery pack, which is having something like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells in series. Okay, it's a 10S. And let's say it is having 3 cells in parallel. All right, so this is an example, a simplistic example of the small battery pack. So this is 10S and 3P configuration, all right? So let's, for an imaginary case, assume that the cell's nominal voltage is 3.6. So you're gonna form 36-volt battery pack, all right? And let's assume it is 2.5 Ah. So you're gonna form about 7.5 Ah battery pack, all right? So if you multiply both of them, you get a power of the battery. So now the functionality of a battery management system is to measure the voltage, all right? So you cannot connect the wires which in parallel. So basically there are about 10 into 3 is about 30 cells are there, right? So you cannot measure the voltage of all 30 cells. It's practically not possible. So what you do, you measure the cells which are in, these are connected in parallel circuit, right? So you measure the voltage across your parallel circuits. So, and then basically you're reading an average of these three, right? And that's how you read the voltage. So individually, it becomes very complicated to because you cannot technically measure when you have the electrical circuit connected in parallel, right? So you would go for the measurement something like this. So you have a voltage measurement, and then you have a current measurement, all right? So current measurement is typically done by a current sensor. If we have a couple of types, one is shunt-based approach, other one is a Hall-based approach. So either you can have a shunt resistor, I'm sorry, yeah, you can have a shunt resistor or a Hall sensor. So that can be used as the sensor to measure the current. So we typically measure the current of the module or at a pack. We don't need to measure at single cells, all right? So we measure at the output of the pack. So then we also have to measure the temperature. So the temperature measurement is done by typically like NTC or PDC type of sensors, right? So you can measure, that's again a complicated thing that, where do you want to keep this sensor? So if you have about 30 cells, are we measuring the temperature of all 30 cells? No, we're not actually measuring the temperature of all 30 cells. We're trying to measure the temperature at some two or three portions are parts of the BMS, sorry, parts of the battery pack. So then you also have to measure isolation. So isolation is something where is the battery pack or the chassis of the vehicle, are they in contact with each other? All right. Or any part of your high voltage circuit is in contact with your chassis. So what happens is that means there is electrical short circuit. All right. Maybe let's say the wire, which is HV wire, is got eaten up by a rat, and that wire is getting contacted with the chassis of a car. So then there is a short circuit, right? So if a person comes inside it and then get electrocuted, so you don't want that to happen. So there is a BMS also have certain sensors which does the insulation monitoring. So galvanic insulation, whatever they call it as. So that it is always tracking, is there a short circuit between your battery pack and the chassis of the vehicle? All right. So like this, there are various different sensors, and through them you measure the voltage, you measure the current, you measure temperature, you measure isolation. All right. So any questions from anyone? So please do drop them in the chat box. So then there's something called as an estimation. So the technical word for measurement and the technicality of estimation, they're very large in difference, right? So measurement is a different word and estimation is a different word. Estimation is like you're trying to relate a value depending upon the data that you have. It is not accurate in place, right? So there are a lot of algorithms which comes as part of it, is a state of charge algorithms and state of health algorithms, state of power, state of energy, state of life. So various different type of algorithms that comes as a part of the algorithms that goes into the estimation. All right. So SOC is where you want to know the remaining capacity of the battery pack. SOH is some parameter you want to know the current state of the battery with respect to the beginning of the battery's life. State of power is something that ability of the battery pack to give an output at that instance. And state of energy is that the amount of energy that can be retained in the battery pack. So state of life is a parameter where you could predict for your repair applications, for the service applications as such, and in a simplistic terms. So then the next is degradation. So you also have to estimate the degradation. Degradation is like compared to the day one of the battery, if the aging has happened, that is something similar to SOH. So if the cell has lost its ability to give an output in terms of power, in terms of the capacity to retain, that would be degradation and aging. So this can be also part of this estimation algorithms. Then we also have to perform something called as a protection. So that is in terms of under voltage protection, over voltage protection, over current protection, under temperature protection, over temperature protection. If the contactors got welded, if there's a short circuit, or many other scenarios, right? That's something like a functionality of a BMS. So what is over voltage protection and under voltage protection? So as we know, maybe I'll just go on to one of the slide. All right, it is good to explain here. So if you take a cell, if you take a battery, all right. So if you take a cell, the cell has a voltage between its full charge to a zero charge. All right. So when the cell is at 0% SOC, let's say it reads about 2.6 volts. Okay, 0% SOC, it reads 2.6 volts. And then you say 100% SOC, which is here, all right, 100% SOC, it will read 4.2 volts. Okay, so then the scenario between these cases is, so the voltage is constantly changing between the bandwidth, something like this. It is very specific to each cell, all right? So each cell exhibits a very unique characteristics within itself. So going back to the topic, which is here, under voltage protection, so over voltage protection, you do not want to let the cell to go below this temperature, so below this voltage, all right? So you want to retain the voltage and stop the cells from discharging below that specific voltage. That is called as an under voltage protection. Under voltage protection. So over voltage is, you don't want to charge the cell above this specific defined value that is about 4.2. All right, that becomes an over voltage protection. There's an under voltage protection, other one is an over voltage protection. Okay, so you can engage the battery management system to do that. So how do you do that? It is by constantly measuring the voltage, and then if the voltage is being triggered below a specific threshold value, you want to cut off the battery pack from the load, or inform the driver that okay, the SOC is going below, so stop the vehicle as such. Similarly, the overcurrent is you cannot draw a lot of current out of the battery, can more than what is it defined for, right? It is just like this. If you're trying to pump the water with a really a large amount of pressure, either you ruin the pump or you possibly ruin the pipe, right? So I imagine for a case that if it is not capable of carrying the amount of current or of water in case of the pipe, so the pipe will definitely undergo a pressure, and then it would start to leak. Similarly at the cell too. So if you try to draw a lot of current out of it, it is having certain limitations in terms of its current collectors. It is having limitations in terms of the interpolation or kinetics of the reactions. A lot of these parameters are there at a cell level. So if you try to draw a lot of current out of the cell, so you tend to overheat the cell, and then you tend to increase its temperature. You can cause a lot of gas formation, and gas formation leads to increase in pressure. Increase in pressure leads to venting. Still increase in pressure would lead to a blasting of the cell or a rupture of the cell, right? So you should not do a lot of discharging. So you should always limit the cell on a specific value of the current. So this is all a lot of OEMs have give you a value. So if you do not have enough research done in-house, you just have to stick to those values. But if you have tested those cells even to take below a specific or higher the specific values, you can still play around. So similarly, under temperature and over temperature, the cell exhibits a very different behavior at specific temperatures. If you take a cell, conduct a test at 25 degrees Celsius, and you discharge the cell at specific current. So the characteristic curve, which is something like this, right? So which you have seen. So let's say this is a characteristic curve. So this curve is at specific T temperature, specific I, that is a discharge current, right? So if you vary any of these two parameters, the characteristic would drastically vary, something like this, or even to a case something like this. So area under this curve represents the available energy from the cell, right? So as a part of this, we need to understand that the cell always have to be within its specific temperature bandwidth so that it can be providing us the maximum output. So if you want to do that, you just have to keep the cell within its safety limits of temperature. So that's why you need to measure and monitor the temperature. So then the concept called contactor welding, all right? So just to explain the topic, I'll just go a little ahead. What is called as a contactor? Okay, yeah. So what is this contactor is? So this is an architecture level diagram. So we have a battery management system here, all right? So there is a batteries here, all right? You can let's define them as a modules. So each of these modules are connected to a slave, all right? The slave is a small control board, right? So they're connected in daisy chain. Do you see this here, right? So SPI type of a communication, and then the data is communicated to a master board. So the data is being collected from the batteries cells and to the slave, and the slave communicates the data to this, and then the data goes to the battery management system. So now the battery management system ensures. Let's imagine that it has identified under voltage scenario that the cells are going below specific voltage. At a cell level, let's say it is 2.6. At a pack level, maybe it is, let's say, a 48 volt is nominal, and maybe it is like 38 volt or something under voltage cutoff. So what happens is that the battery management system have to stop the cells from discharging or modules from discharging, right? So how exactly it does? So it has set of components such as this. So you can call them as the contactors, right? So what exactly it does is it just sends a signal to any of this contactor. Contactors are like relay, right? So it sends the signals to them to disconnect the battery from the rest of the uh, load system. So that is how the protection will happen. So this is in terms of under voltage. When you are discharging a battery pack, you need to disconnect it if you are going under voltage. It is not like an abrupt discharge. We call them with a specific term called steefing. Uh, so it's like if your vehicle is, let's say, at a specific velocity, we can't just cut off the battery pack, right? Or else, like if you're on a highway, you're going at 100 kilometers per hour. If you directly cut off your battery, then you definitely will not have a good experience, and possibly you're going to meet with an accident. So you don't want to do that. So you would like call it a tapering. So you know at your specific value you want to trigger the information to the customer and keep warning them that you have been limited with the vehicle speed of this much. And then if you go to a specific voltage level, it's for interpretation to a customer, it will be SOC, right? You don't want to read him a voltage. You get confused about if you read a voltage to him, right? So you would read a value of the in terms of SOC. So if when you reach about 20% SOC, you tell to a customer that your vehicle speed is limited at a maximum of 40 kilometers per hour. Then you can go to a 10% SOC. You tell the customer that it's been limited to possibly about 30 kilometers per hour. So then, like that, you inform the customer that you limit the value of your output speed at the motor. Then that's how you can control the part of your uh, you know uh, system to ensure that you don't just cut it off abruptly. You go through like a tapering approach. So then in similar, you can also think that contactor has got welded. There is a scenario, maybe you can just Google it out, what is called contactor welding. So the concept of contactor welding is this, that you have to, check if this contactor has been welded. So the meaning is that I think if you know the part of a relay as a circuit, so there is a switch side and there's a coil side, right? So so for a bad instance, let's say when the contactor got here because of a high current and a voltage, it might have got welded. It means it has got permanently contacted. So when the BMS has asked it to disconnect, it wouldn't have got disconnected. So now when you have a scenario, so it is already in a on stage, right, without even getting a signal from the battery management system. So in that scenario, so it is called as a contactor welding. You need to monitor all these things. There are algorithms also uh, to do that for, for to engage the contactor, to disengage the contactor, or check if the contactor required to be um, in a good stage or a bad stage. So apart from that, you will also have some other scenarios where it is called as a short circuit, or also and other scenarios. Short circuit is something where if your vehicle have got a short circuit, you need to disconnect the battery from the scenario, or you made an accident in the car, so you should have the battery disconnected from the load. So all these things are done through a contactor. So again, those protections are done by a battery management system. So then similarly, we have balancing, which is called ensuring that all the cells in the pack are being possibly at a same voltage or a same SOC as at that moment. Because what happens is when you have multiple cells, it is impossible to have all the cells at same voltage exactly. So you will have some disparity between the voltages of each cells, right? So the balancing is thus that, for example, let's take what is the issue. This is reading 3.2 volts, and let's say this is reading 2.8. This is reading 3.2, and this is reading 3.0. This is reading 3.2, 3.2, 3.1, 3.3. So if you take the all these values, right? So each cell have a different voltage. This can be because of the cell's manufacturing issues, or because of certain issues in the circuit too. So they ensure that you need to have all of the cells possibly at 3.2. That is an objective, right? Or you want to have all the cells coming to 2.8. So if you want to bring the cell which is at 2.8 to 3.2, you need to charge the cell, right? So how do you charge it? So you just have to possibly do that by removing the energy from another cell and adding the energy to that specific cell so that you can charge the cell. And that is something called as an active balancing. And passive balancing is something that you want to bring all of this 3.2 to 2.8. Okay, so you need to have a resistor, and then you discharge all the cells and bring them to a 2.8. So that's how you do balancing. Because if you have a 2.8 cell in the series pack like this offers some more resistance, and 2.8 is possibly like a 2.6 is the cutoff voltage. It means that specific one cell would come to a under voltage value. So you don't want to have one cell which is under voltage and other cells are still in the better voltage ranges. So that would be a problem for the pack. So you need to ensure that the balancing is done. It means it is equalizing all the cells, which are in the series, in the parallel network. All right, that is what is cell balancing. Then communication. So as I said, you have to have a communication between your master and a slave, and slave and the slave. You need to have a communication between, like for an example, if you take here, you need to have a data communication from your current sensor through a CAN communication protocol that is sending a data to your controller. Like in similar, you can have data communication from the ECU, so from the BMS to a VCU, which is a vehicle control unit, which is say can call it a vehicle CAN bus, which is mentioned here as a part of it, right? So like in similar, you need a data communication with your VCU with the other BMS if it is there, or if it is it's also called as a, it's not a BMS, it's a body control module, BCM. Then it is also an HMI as a part of it. All right, HMI is basically something like your dashboard or instrument cluster. So you need to have a communication protocol. It means data transfer. Also, you need to have diagnostic services that forms industry grade BMS. Because if there is any fault in the battery management system, it should be able to identify that fault and then send that or store that fault and then send it to the user, or give a diagnostic warning to the user that, okay, the battery has come for a repair or a service, or it is under over temperature, or it is under lower temperature critical value. So all these things has to be done through a diagnostic services. You can call it as a UDS, which is called a Unified Diagnostic Services. You can go to this specific ISO 14229, so which talks about diagnostic services as such. So any automotive grade OEM would need to have this, and also on top of this, you need to have ASIL, which is basically an hardware level uh, standard. So you need to select certain components to meet that specific ASIL standard. You also have AutoSAR, which is an architecture for a AutoSAR. Yeah, you need to have a specific architecture of AutoSAR to ensure that you have a commonality of all your software to be maintained at this specific standard. So like in similar few other things will also come as a part of it. So anyway, this is all on the functionality. So this is the functionality of a BMS. So you need to measure the data from sensors. You need to perform estimation. You need to perform a protection. You need to perform cell balancing. You need to also have a communication. You need to also perform a diagnostics. And then that is all forms the battery management system as together. So we have discussed about this slide. So I will just talk about one of this part as estimation. Again, not in very much detail, this is just to give an overview what really happens. So estimation algorithm is something like this. Okay, so the battery behaves non-linear in nature. So the non-linearity is something like this. So if you have a predictable algorithm, the data just goes like this. It is so easy, like you can just write a one differential equation or a simple equation, and then you can understand its behavior, right, as a line, or if it is a parabola, if it is a hyperbola, or in some specific fashion if the cell behaves, all right. So you can predict the scenario of the battery, but the problem is the battery is not so easy to understand. It is very complicated in its behavior, right? So it starts somewhere here, it can go through all these complex things, and there are a lot of influencing factor. Okay, so for an example, let's say the SOC, right? So the SOC from here to here has a lot of influences. Maybe it is have an influence of temperature, it is have an influence of discharge current, it is have an influence of cycle life, it is also have an influence of what I can call it as the SOC, like the previous stages where the SOC has been stored. It is also have an influence on how it was been abused at the past. So a lot of scenarios like this will form and scenario to predict an SOC. So that would be very complex in its own, way to perform an activity. So what you do, we use some algorithms to perform something called an estimation. So it is not something like this. We're trying to fit a curve somewhere in line by absorbing all those variations as such. So basically, the behavior of a cell is highly nonlinear in nature. So that's why you have to perform a lot of approaches to define its characteristics. So let's kind of understand maybe one of the specific characteristics like that. So if you have seen the characteristic of the lead acid battery, okay. So the ideal curve of a lead acid battery would fall something like this. All right. So the meaning is, let's say this is voltage and this is SOC. All right. So this is a 100% SOC. All right. This is a 100% SOC, and this is a 0% SOC at this place. So this, let's say it reads some value, possibly it reads about 1.2 volts here. It reads about 0.6 volts here. So, if you want to measure an SOC, the curve is pretty linear for you, right? So you can just draw the reference lines, and then you say this is 80% SOC, this is 60%, this is 40, this is 20, and this is 0. And this is quite straightforward in a nature how the lead acid battery behaves, right? But the lithium ion battery doesn't behave like in this linear nature. It behaves quite non-linear in nature with various different chemistries. So this would look linear at one specific test case. Again, if you conduct these tests at various different current values, various different temperature values, this curve will not come the same way. They will be coming in a different way. So what happens at this phase is, how do you fit all of this behavior? Maybe the battery behaves on the day one differently, and the battery behaves on a day 365 differently. But the objective of your algorithm is to take all these variations into consideration, predicts its SOC. That is the end goal of a algorithm, all right? So to perform these estimations, we use various different approaches. This is basically part of SOC, all right? So we can use a open circuit voltage approach, or you can use a Coulomb counting approach, or you can also go for a Kalman filters, or also you can go for a machine learning and AI based approaches for the SOC estimation. So what exactly these things are? There are different methodologies to perform either any of the estimation algorithms. So it could be SOC estimation, or SOH estimation, or SOP, or SOL, or any of those estimations that you want to perform. So these are the various algorithms which are involved. So I will just dive in to a few more slides where I would just be able to summarizing what all engineers does at making a BMS. So that part of all my discussions till now will be summarized here as in the outcome. So making a BMS, so there are various engineers involved in designing and developing a battery management system. So one is your application software. What I told about SOC, SOH, SOP, and all your state machines, all that comes as a part of your application software. All right. So that is basically you can do a 1D modeling using tools like MATLAB or Embed, or you can also go for Altair based 1D tooling, 1D based models, or you can also go for any other tool sets that are available in the market. So where you can build your application software, where it takes care of estimation algorithms or state machines, it takes care of protection, it takes care of anything that comes as a part of your application software. So the application software can be developed by understanding the cell properties, cell characteristics. So that is an area where the battery experts comes in. All right. So somebody who's a battery expert can be from background of mechanical engineering. He can be, or she can be from the background of electrical engineering, or also from chemical engineering. So somebody need to be a subject matter expert to tell that the way the battery behaves. So that those are the first guys whom you need to have if you want to develop a BMS. So if you want to be an expert in that area, so you can work as a part of your battery expert team to create these algorithms. So you can either do them either, you can make them in MATLAB, and then you can convert that into a C code. You can use MATLAB and MATLAB Simulink and perform that, and then you can convert it to a C code, or there are a lot of ENC guys who would write that, complete your algorithms in embedded C directly. But nowadays, typically people use MATLAB because of the complexity of the models and to perform like mill, SIL, and hill and everything together. So then you need to have experts of a communication protocol, so who can build your CAN communication stacks, who can also take care of porting your controllers, because you need to put the control algorithms into the um, uh, embedded hardware. So that there are communication protocol experts who can take it either through a JTAG or through a CAN, or you need to build that CAN network to connect with all your components, or a master and slaves, or any of your sensors, or even to the vehicle as such. So you need a communication protocol experts. So then you also need an expert to interface an application software on a target controller. So that is where it comes as a device drivers. All right. So the device drivers are like, if you have a sensor that is reading a value, and you need to tell to a controller that, okay, this is the value that you have to read as a temperature, and this is the value you need to read it as a voltage, there's a value read it as a current, and basically you need to integrate your application software into the controller so that the computation or a processing can happen. That is where you need experts from a specific tool chain. For an example, if you're selecting NXP, if you're selecting TI, or any of other control chips, right? You need to have those guys who can actually interface your application software to the embedded controller. So then you have functional safety experts. Functional safety is an area where you need to ensure a fail-proof design for your system. So you need to have an extensive test cases where you can check that what if this can go faulty? What if this can be abused at various different scenarios? How do you assess the failure criteria for that scenario? All right. So depending upon all those scenarios, you need to ensure different layers of security or a safety. Let's say, for an example, temperature sensor fails. All right. Let's say, for an example, current sensor fails. So what is your risk mitigation possibly? Do you have another sensor to measure current? Right. So all the scenarios will come as a part of your functional safety. So that is a very prioritizing activity for any of the OEMs today, because that's why if you see a pedal position sensors, which is basically your accelerator pedal sensor, so there are two sensors, right? So it's basically if one goes faulty, so you have another one that can kick in to take care of that scenario. So that's where the functional safety experts comes in. Then you need to also have an AutoSAR experts and the ASPICE experts to come to form your algorithms into a structure. And then we have experts who can perform. Mill is basically part of your, the 1D modeling. SIL is where you have to target your, algorithms to a specific hardware and test if the algorithms really run well in real time. Then you need to also have a Hill experts that they can test the application software or also your target controller. Does it really function as it is defined to perform in every scenario? All right. So that's where you can call as a test experts. Then you also need to have a software testing, because you are developed algorithm, you need to perform a testing, so that you could do as a part of your SIL, also part of the Hill. So then you need to have a PC-based calibration software design. So you have developed a ECU, right? Let's say call it as a battery management system. So not everybody knows embedded C to do a perform calibrations, right? So you need to have a PC-based software, which is an interfacing software, so that you can connect your BMS to the laptop, and you can see as a calibration engineer to perform certain calibration activities, because you can't just go every time and calibrate your BMS for a specific requirements. So you need a PC-based, like a Windows-based or a Linux-based or a Mac-based user interface software developers. Then you also have a real-time testing and calibration engineers, all right? So they all perform and form into a BMS development. So then the other side is the hardware architecture. Somebody to be a hardware architecture expert. The hardware architecture expert is, I told you about, like a centralized BMS selection, distributed BMS selection, communication protocols in between them, a specific way you need to interface all your components. So these are all the architects who have a very large expertise and failure scenarios in their past, and they accumulated all the knowledge to architect your BMS to perform really well in all scenarios. Again, a functional safety expert at hardware level. PCB designer obviously will take care of ECAD, and then you have EMI EMC compliances for the interferences of the network, interferences with respect to magnetic field. You need to also have a fabrication guys who can take care of PCB fabrication, hardware testing, and then the large scale manufacturing. So they all will constitute a form development to make a BMS into a reality. So at Decibels, we also partnered with a company called Sloki, which is based out of Bangalore. So we have collaboratively working on developing a scalable distributed battery management system. The Sloki is expertised in hardware design and hardware development. We are trying to bring our expertise with the 1D modeling, which is basically algorithms such as SOC, SOH, SOP, and various different algorithms, and also state machines to integrate on hardware and provide a BMS solution which is made in India and localized in India to some of the suppliers. So yeah, this is in R&D stage currently right now. And then we also have courses at Decibels Lab, so where we can help you to learn the design of BC battery management system, either on the software side, also on the hardware side, like an algorithms, and one side on the algorithms, other side as the embedded hardware design as such as a PCB design. So we have programs if you would like to explore. We have some of the interesting activities. My team will share you at the last end of the day. So if you have any questions, the floor is open for QA. And that's what I was intended to deliver as a part of this session today on the battery management system. So any questions, if anybody have, so floor is open for QA. I think we overran today's session by many minutes, about like 10, 15 minutes. So yeah, floor is open for QA. If anybody have questions, kindly do ask questions. Okay, so kindly share the slides. All right, guys, I might have used some data from the internet, so which may not be, which may be subjected to copyrights. So I wouldn't always intended to share that, to just keep a respect to. You can see some of the places I mentioned, the company names, or where I got an images from. So with that, I would possibly try and check if I can remove some of them and show you the slides. So what is the meaning of active and passive balancing? Passive balancing is, okay, so let's just try to draw this and quickly run through the active and passive balancing. So active balancing is a concept. Let's say you have 3 cells. Okay, so this cell is reading, let's say 3.2 volts. Okay, and this cell is reading 2.9 volts, and this cell is reading 3.2 volts. Okay, so they are in an imbalance stage, correct? So the objective is to balance all of these cells together. And so there are 2 ways that you can do it. You can discharge this cell and this cell, so bring it back to 2.9. So how does the discharge really happen? The discharge will happen. You can connect a resistor to this bank, which is in parallel. All right. So you can have a MOSFET. You can have your FETs to come in here, and then on the FET, and the FET would redirect that to a resistor, and this resistor will dissipate, draw some current, and dissipate that as a heat into environment. All right. So what happens when you dissipate? The voltage drops down, and until you dissipate, until it comes to 2.9. All right. So you do the same thing for here. That's why if you have 13S in parallel, you have a 13 set of dissipating resistors. Okay. So all of them can be connected to each of the parallel circuits. So you connect here, you connect to this one, then you just dissipate that energy out of the cell, and then you bring them back into the bring all of them into 2.9 and 2.9. This is called passive balancing. All right. So this is one of the approach. So if you want to go for an active balancing, so there what you do is you don't want to dissipate. Basically, what you do in passive balancing is you waste the energy in form of heat, right? So in active balancing, you draw some amount of energy from the charged cell, and you put that energy into this cell. Okay, you take some energy from here, you put it at this. Okay, so that is a active balancing, and that is a little more complicated because you need to also ensure that this cell is, you're drawing exact amount of energy from this cell, you're drawing the exact amount of energy from this cell, and this cell is being charged, and that comes back to, let's say in this scenario, you want to bring that up from you're supply to 3.2, and you're supplying 3.2 from here and to a cell which is at 2.9, and by the time it reaches a specific value, possibly this has become, let's say, 3.1. I understand it's still not 2.1, 3, it becomes 3.1. So this cell has become 3.1. This cell has, which has 2.9, has become 3.1. This cell has become 3.1. So you balance the whole cells, right? So this is a way you are able to make it through an active balancing. So the passive balancing is dissipate an energy. Active balancing, you bring the energy from one cell, put it into another cell. So that is basically happens in the cell balancing. I hope I answered that question. Okay, cell balancing is done while quick charging also. So what happens? Okay, when is it done? All right. So the cell balancing is done typically by end of your charge cycle. Okay. So it should be done ideally at all scenarios. Okay. So charging is done with various different protocols, CCCV, CPCV, various. This is standard one, which is proven. CCCV is like, this is the constant current and then constant voltage. So you're trying to supply the current to the cell. The voltage of the cell keeps going higher and higher and higher. You come to a point where you reach a saturation of the cell's voltage. Then you spend some amount of time in normalizing yourself at the last to ensure that there is a saturation at your cell in terms of charging. So this is a part of the time where you can also perform your balancing, and even after a certain charge time is over, you can also perform balancing. So is it done typically? Ideally, the cells should be balanced at a very given point. You have various complexity to answer that how much percentage of imbalance is there, whether that imbalance need to be addressed to mitigate any risk. So all these parameters will come to define whether the balancing should be triggered or not to be triggered. All right. So if you're doing a fast charging, yes, you did it, and then you have a very large imbalanced cells, which are above your risk value. So you need to assess that scenario, and then obviously you have your algorithms to take care of that. You assess those possibilities when you're developing your software, and then you're mentioned in application software that okay, if this is a scenario, you need to go for a balancing. So yeah, that would be a case to case study. Right. So great. So I just let me know if the session was good or if you're expecting something apart from what I was delivered as a part of the today's topic. So would be very glad to also address and improve the sessions upcoming in tomorrow. So what happens to the master BMS if one of the slave BMS is malfunction since they are not connected through a CAN system? Will the communication stop? All right. So yeah, obviously you would have a fault in the system if the slave is not communicating with the master, and obviously you don't intend it to make any further communication uh, with the master BMS. Then you would definitely have to trigger a malfunctioning. And if the communication has been, see, typically if you take CAN, it's very highly uh, uh, you know rare scenario that you would have an issue with communication, and so you would not have any of those worst cases coming in always. But if you do have, then you would definitely trigger a malfunctioning, and then you would have to definitely stop. So can it be also done in Scilab as alternative to MATLAB? Scilab, you can definitely try to definitely build it because it's also equally competent. But if you are running a very large model, it tend to fail. Something like an extended Kalman filters and all, if you try to do it in Scilab, it would possibly fail. It would possibly, hang up itself at most of the scenarios. But certainly you can do design your equivalent circuit based models with a 1RC or 2RC circuits. So if you are okay, do also explore doing in Python. You can also develop in Python too. Great. So awesome. So it looks like that's pretty much of all the questions which have been put up here for the QA. So if you have any inputs to me about the session today, so kindly do share your feedbacks. So on the chat box, I will be quite happy to improvise them in my upcoming lectures. So I hope the session was good and I hope the session was interesting for all of you. Um, Thank you very much for everyone for taking part in today's session. It was fantastic interacting with you and look forward to engage the sessions in upcoming days. Also make them similarly interesting and similarly exciting for all of you. Thank you very much, everyone, again. Um, that's pretty much from my side for today. All right, then. So, time to say goodbye and good night to all of you. And continue your learning and enjoy your learning going ahead. With programs at Decibels Lab, also there's a lot of content available in many different platforms. So definitely enjoy learning. Thank you very much again for everyone. Good night. Take care. Bye bye. See you tomorrow.